Hi everyone, I am Marco Vizcarra and today I will be presenting Microsoft Phi-3 technical report, which introduces a family of small language models that challenge a core assumption in our field, that strong performance requires massive scale. The headline result is that a 3.8 billion parameter model small enough to run on a smartphone matches GP3 3.5 and Mistral AX7B on key benchmarks. I will cover the training philosophy, model architectures, benchmark results, extensions to multilingual, long context, and multimodal settings, and finally, safety alignment and limitations. The central insight is simple. Phi-3 Mini has just 3.8 billion parameters compared to Mixtral's 45 billion, yet the two perform similarly on most benchmarks. The difference comes down to training data. The team curates a combination of heavily filtered public web data selected for educational quality and synthetic data generated by larger language models. This builds on Microsoft's earlier textbooks are all you need line of research, where Phi-2 at 2.7 billion parameters matches models 25 times its size. Phi-3 takes the same philosophy considerably further, and the implication is clear. With the right data, you need far fewer parameters than conventional scaling laws would suggest. Now let me walk you through the full model family, 5 models in total. Phi-3 Mini is the 3.8 billion parameter base trained on 3.3 trillion tokens and small enough to run on a phone. Phi-3 Small at 7 billion introduces a block sparse attention mechanism that distributes different sparsity patterns across heads to reduce memory usage. Phi-3 Medium at 14 billion is the largest dense model. Then there is the 3.5 series. Phi 3.5 MOE is a mixture of expert model with 16 expert networks, only 2 active per token. So you get 42 billion total parameters, but just 6.6 billion at inference time. Phi 3.5 Vision adds a clip image encoder for multimodal tasks. Finally, and importantly, all 5 share the same tokenizer and training philosophy, which keeps the ecosystem unified. One design choice that is especially worth highlighting is how practical Phi-3 Mini is from an engineering standpoint. Rather than introducing a completely new architecture, the team intentionally kept it very close to Llama's 2 block structure using the same tokenizer and the same overall layout. As a result, existing Llama 2 tooling, inference stacks, and quantization pipelines can be reused immediately, with little to no additional porting effort. Looking at the model itself, Phi-3 Mini includes 32 layers, 32 attention heads, a hidden size of 3072, and a vocabulary of about 32,000 tokens. In terms of context length, the standard version supports 4,000 tokens, while an extended 128,000 version is enabled through long-row positional encoding. Most importantly, from a deployment perspective, the model becomes extremely practical at 4-bit quantization. It fits in roughly 1.8 gigabytes, and that compact size is what makes on-device inference on a modern smartphone realistically possible. This is probably the most important conceptual slide in the presentation. Most labs think about training in terms of compute, either scaling the model to match available resources or training longer on the same data. Microsoft takes a different path. Instead of only scaling compute, they focus on improving data quality for a fixed model size. That leads to a somewhat counterintuitive choice. They remove content like sports scores and daily trivia. For very large models, that data is fine, but for smaller models, it can be a waste capacity that could be used for reasoning. So training happens into two stages. First, broad web data builds general language understanding. Then, more filtered data and synthetic examples makes reasoning and specialized skills stronger. This chart makes the main point very clear. If you compare the slope of the phi curve with Llama 2, the difference is striking. Phi-3 mini with 3.8 billion parameters reaches a lower MMLU error rate than Llama 2-13B. Even though the Llama model is more than 3 times larger. Phi-3 small at 7 billion parameters also outperforms Llama 2-7TB. What makes this especially interesting is that the two model families come from a broadly similar architectural lineage. The big difference is in the data. Llama 2 was trained on a more standard fixed web dataset, while Phi uses a curated, filtered, and synthetic augmented pipeline. So the takeaway is clear. With better data, you can get stronger results even at a much smaller scale. Now let's look a bit more closely at the benchmark results. On MMLU, which measures broad knowledge, Phi-3 mini scores 68.8, not far from GPT 3.5 at 71.4. On GSM-AK, which tests math reasoning, Phi-3 mini actually does better, scoring 82.5 versus 78.1. On empty bench, a measure of conversational quality, the two models are essentially tied. The larger Phi models improve even further, with Phi-3 medium reaching 78 on MMLU and 91 on GSM-AK. Overall, Phi-3 mini averaged 69.7, outperforming Mixtral and coming close to GPT 3.5, despite being only a 3.8 billion parameter model. Next, let's turn to the Mixture of Experts version, which is one of the most efficient designs in this model family. It includes 16 expert networks, but importantly, only 2 are active for each token. As a result, even though the full model has 42 billion parameters, only 6.6 billion are active at each inference time. In addition, the routing is handled by sparse mixer, which makes expert selection smoother during training. In terms of performance, Phi 3.5 MOE scores 78.9 on MMLU, slightly above GPT 4.0 mini at 77.2, while also reaching 88.7 on GSM-AK and 70.7 on human eval. Overall, it clearly outperforms Llama 3.1 AB and remains competitive with Gemini 1.5 Flash. So the key takeaway is that this architecture delivers strong results with far fewer active parameters per token. Another important improvement in the 3.5 series is that it addresses two limitations of the original Phi-3 mini: limited multilingual support and a short context window. The original model was mostly English and supported only 4,000 tokens, while Phi 3.5 adds more multilingual data and extends the context window to 128,000 tokens using long rope. As a result, multilingual performance improves substantially, and the MOE model also performs strongly on long context and code understanding benchmarks. One important limitation remains: performance still drops at the full 128K length, which the authors attribute to limited long context training data. This slide highlights the practical deployment story. When Phi-3 mini is quantized to 4 bits, it uses only about 1.8 gigabytes of memory. The team showed that it can run on an iPhone 14 fully offline, with no cloud connection at all, while generating more than 12 tokens per second. That is fast enough for a responsive user experience. The bigger point is that a GPT 3.5 class model can now run directly on a consumer phone, which is especially important for privacy sensitive applications like healthcare or enterprise tools. Next, Phi 3.5 Vision brings the model into the multimodal setting. It combines a visual encoder with the Phi 3.5 mini text decoder, allowing image and text tokens to be processed together. A key feature is dynamic cropping, which helps to handle different image sizes and aspect ratios more effectively. It is then trained on a large mix of image text, OCR, chart, and table data. The results are impressive. It scores 91.3 on Science QA and 81.8 on Chart QA, beating GPT 4.0 on both while using only 4.2 billion parameters. Safety alignment was also a major focus in Phi 3.5. The process was iterative. First, supervised fine-tuning on responsible AI data, then direct preference optimizations to reduce harmful outputs, followed by adversarial red team testing to uncover remaining vulnerabilities. Those findings were then used to generate more target training data and repeat the cycle. As the chart shows, this led to large reductions in harmful responses across all categories, while benchmark results also indicate that the model became substantially more factually grounded than Phi 2.
Now let's turn to the limitations. To the author's credit, the paper is quite candid about them. First, Phi-3 Mini has only 3.8 billion parameters, so it cannot store as much factual knowledge as much larger models. That becomes clear on Trivia QA, where it trails GPT 3.5 by a significant margin. The paper does point out that retrieval augmentation can help, and it even includes a working web search example. Another limitation is language coverage. The mini model is still mainly English, and even the 3.5 series remains behind frontier models on multilingual tasks. Hallucinations also remain an issue, especially for the vision model in sensitive areas like finance. Finally, long context performance still declines as the input gets longer, which the authors identify as an important area for future work. Finally, I would highlight five main takeaways. First, high quality data can partially substitute for scale. Phi-3 Mini at 3.8 billion parameters performs surprisingly close to models much larger than itself. Second, on-device language models are now practical, responsive, and fully offline. Third, mixture of experts architectures provide an excellent efficiency trade-off by offering large capacity with far fewer active parameters at inference time. Fourth, multimodal capability does not require huge models, as Phi 3.5 Vision demonstrates. And fifth, safety alignment throughout supervised fine-tuning, DPO, and iterative red teaming produces clear, measurable improvements. Overall, this paper suggests that the future of AI is not just about making models bigger, but also about improving data, designing more efficient systems, and expanding real world accessibility. Thank you for your time. And in summary, the Phi-3 family shows that with high quality data, small models can achieve capabilities that were once limited to much larger systems. This opens an important opportunity for on device AI, stronger privacy, and more accessibility. Thank you.